Lango College.
Good evening, everybody. Let's
Yes,
humble
good
ourselves.
evening.
Let's humble ourselves and we pray. In the name of the Father, the Son, and the Holy Spirit. Father, in the name of Jesus, we thank you for this new day. We thank you for the gift of life. We thank you for the students. Thank you for the facilitators and the coordinators. Father, we appreciate you that we have gathered in your name for the beginning of for the for the beginning of wisdom. We find it from you. Father, I appreciate you. May you guide us from the beginning to the end in Jesus' name.
Amen. Amen.
Okay, thank you so much for the word of prayer. We are very grateful to have all of you here, and thank you so much for keeping time for this session. Let me hope my microphone is clear, and I want to remind you that we shall continue to use this same link, same room, every day up to Friday from 4 to 6 p.m. unless otherwise. At this point, allow me to welcome our facilitator of the day, Teacher Ahewa William, to do a microphone check and then to officially start off the session.
Hello there, can you hear me?
A bit more.
Yes, Mr.
Teacher
Kaziwa,
Ahewa?
I don't know if I'm loud and clear. I don't know.
Okay, like the microphone looks not to be so clear.
Let me try doing some adjustments. I see.
Are you using headsets?
Yes, I was using headset.
Or maybe we can first have the headsets off and then we check on the microphone.
Okay. Can you hear now? There, can you pick me?
Okay. Maybe let the people in the chat also let us know. Okay, you are not so clear.
Still checking. See why is it not speaking? Why is it? It's supposed to be very loud and clear, especially when I'm using the headset.
You are saying?
I'm wondering why it is not being very clear, yet I expect it to be very loud and clear, especially when I'm using headset.
Okay. I don't know.
Let me test again headset.
Yes?
I'm trying to test again and
Okay, first check again and see.
Mr. Kaziva, has it improved? Those in the
Yes?
chat, you can try. Has it improved? Any improvement?
Not yet. Not yet.
Let me first disconnect it, then I connect it again.
I think Teacher Hewa, let us start, and then we shall sort it along the way.
Hello?
Yes?
Is it a bit clearer?
Okay, a bit clear.
It is not a bit clear.
Yes.
Maybe those members can tell us if it is not a bit okay, then we proceed.
Okay, I think we can start, no problem. I think, okay. We can start, Teacher Hewa.
All right. Let me see if I'm going to share my screen. Can you get my screen? Mr. Kazira, I don't know if my screen is clear.
Your screen is visible now.
Okay. All right, members, very good evening and welcome to today's session where we are going to be interacting or sharing ideas specifically in the physics practical. That is the physics 535 stroke 2 and the 3. As we may already be knowing that this paper, due to numbers in schools, in most cases, it is normally um, it is normally it is normally shared. You find you have some students doing paper 2 and others doing paper 3. So, but the content remains the same. And today, your facilitator is none other than teacher Ahewa William, and I'm a teacher of physics and mathematics. So on YouTube, those of you who may be interested in, I make some content in especially physics, and I share the videos on YouTube. So I use the name Chahewa William. You can always get there and you check and see the videos I make. So without wasting time, let me start by showing you what the paper format is or how the paper format looks like. We have this paper, the paper code is unchanged. It remains the same, 535 stroke paper 2. All those who do paper 3, it is 535 stroke paper 3. And the element of construct, of course, under this physics, under this part, under this paper, is basically we are looking at the student's ability to conduct a scientific investigation. So you might be knowing from your science background, science and meaning, physics, biology, chemistry, you must have looked at what conducting a scientific investigation or the steps for conducting a scientific investigation, what it requires. I don't know if my audio is very clear. If there is anyone who can maybe give me a hint.
Yes. Now, teacher Hewa.
Yes, please.
Yes, I think the audio is not so clear. I don't know whether you have an external sound that you have connected, like the voice.
Like I've connected in which way?
Yes?
Like I have connected in which way?
Like, are you using just a laptop?
I'm using laptop with my Bluetooth headset. So
With your?
Bluetooth headset, the headset.
I think the Bluetooth headsets are the ones bringing the challenge, maybe. I don't know that we can first disconnect them and test and see.
Okay, let me try disconnecting them, then I see if it will help, because I don't want to.
So I don't know if that one is
Very,
better or
very clear. Perfect.
okay, good. So let us proceed. I was saying that the element of construct under this paper is conducting a scientific investigation. And so we'll be looking at how a learner can carry out an investigation and probably solve societal problems or challenges. And oops, yeah. And the paper, as you may already be knowing, it will have two items. That is, say it will have mechanics, the two items, each item the item can be coming from any of the three topics, that is mechanics, light, and electricity. So unlike the previous format, where we would have mechanics being compulsory, and then we have the light and electricity being optional, this time NCDC changed and it made all the three topics to be optional. However, you have to take note that the paper will be having only 2 items. And these 2 items can potentially come from any of these 2 topics, any of these 3 topics, sorry. In other words, the paper may have a number or an item coming from mechanics and another one coming from light, or the paper may come having a number from light and another number coming from electricity, or it may have a number that is in mechanics and another number coming from electricity. So we need to be knowing that the 2 numbers or the 2 items may appear from any of those. So we therefore would like to discourage students who may want to, let's say they call it overcramming or spotting. Those who want to spot, they say, me, I'm focusing on only this topic and this topic. I want to tell you that the paper may come when the topic you have focused on is not in the paper. They've brought the other 2 that you did not prepare for. So it is better and advisable that you prepare in all the 3 topics. Good enough with the practical, we just maintain the skills. We look at the skills. How are the skills of the learner? We are looking at the ability of the learner, how you can manipulate the apparatus, how you can carry out the investigation to solve a given challenge. The student, from those 2 items, you may already be knowing you're required to attempt only 1 item. The duration of the paper is 2 hours. Remember, initially it used to be 2 hours, 15 minutes. Now it has been reduced to 2 hours. So, but remember, on those 2 hours, it is important for you as a student to have 15 minutes of preparation. I don't know. Is that mode okay for you? Is it clear, or you leave the other mode? Hello?
You are clear, Teacher William.
I'm meaning the mode, especially the screen. I don't know if that mode is okay for you.
The screen is okay. The screen is okay.
You see, I've splitted it now, like I'm having presenter mode.
Yes, it is better.
Okay, good. So I was saying that the duration, the time will be 2 hours. So if we still, as we continue looking at the paper format, what are the nature of the items? First of all, the item will contain any of the following. It can contain a scenario or a situation. It will contain tasks, and then it may or it may not contain a hint. I'm very clear there that the item that you meet for a practical, it may not have hint in it. So it is important for the students to be ready to attempt an item where either a hint is given or an item where the hint is not given. Now, if we look at what do we expect you now to give as a student or a learner, or what we can call the expected learner's response. 1, after looking at the item, you've read through the scenario or the situation that is before you. You've looked at the task that they require you to do. You will now be required to give a report or a response or the answer. So the report, we expect in that report, you must include an aim of the experiment. I'm going to go in detail and we explore more these parts of the report. And finally, I will show you a sample of a practical, a sample item, and even I leave you with some others for your practice. So you're expected to give the aim of the experiment. You're expected to state the variables that you're going to be dealing with in that experiment. You are also expected to give the hypothesis, prediction of what you expect to get, or basing on previous studies, what is known. And obviously giving the procedures. Now under procedures, we expect there you will be including, you'll show us the list of the apparatus you've used or you're going to use. You'll show us the diagram. You have to draw the diagram, and then you give the steps that are followed when doing this practical. Then you'll also, as a learner, you're required to give the risks or the sources of errors, and as well as the precautions that you're supposed, let's say a person is supposed to take care of if he or she is to minimize the sources of errors. Then after the risks and sources of errors, of course, you are expected to present your data, and the data presentation is better in a table or in a tabular form, like when you put it in a table. I believe most of these you might have already interacted. The teachers might have already shared them with you. I'm just sharing them for purposes of emphasis. So we also expect, or you're expected to analyze and interpret this data. Now, how do you analyze? You give, of course, you will have a graph, and that graph is not there just for decoration. It is there to help you analyze the data that you collected in an experiment, and then the calculation helps you also do the interpretation and aid you in making the conclusion, and subsequently advising on the situation or the task that is at hand. So basically, those are what I can say, like the eight parts that make up your report. They are like the 8 parts that form up your report, whereby in those, if your report has those 8 parts, then we expect you to be showcasing the skills in those different parts. Like I told you earlier, the main, what I can say, what we are calling the element of construct now, ability of a learner to conduct a scientific investigation. If you look at these 8 steps we've talked about, they all bring out your abilities in different areas. There is a part where you'll be required to handle the apparatus. There is a part where you're being required to manipulate the data. There's a part where you're being required to interpret the data. If you realize at those 3 skills, I can call them skills, they are all part of scientific investigation. So let's dive deep now. We look at part by part. What do you expect? What or how does each part look like? When we start by looking at aim of the experiment, under this aim of the experiment, here we expect the learner is expected to state the purpose, and then you state the investigation, then the purpose. Like, what are you looking for? Why are you looking for it? That is in the aim of the experiment. What are you looking for, and why are you looking for it? Or what are you trying to find? That is what what you are looking for is what we've called the investigation. And then why you are looking for it, that is the purpose. I've given you here an example. Like if you say an experiment to determine the spring constant, that is what you're going to look for in the experiment. You're going to look for the spring constant. Then now comes the other part. Why are you looking for the spring constant? That is the why part. Now that is the purpose. Now, this is where it comes in. You're looking for the spring constant in order to determine whether it can be used to replace a damaged one. Okay, just ended there, but you can add on a damaged one in the umbrella, a damaged one in the weighing scale, depending. So, but you realize your aim should be comprising of these 2 areas, stating what you're looking for and why you're looking for it. Then, when it comes to variables, now variables is a big, I will not say big area, but it is in some way, it forms the backbone of this experiment you're going to conduct, or the backbone of the practical. Because without variable, if you don't get to identify earlier, it is the variables that you're going to use. Or when you know what you're going to look for, then you must know how will you get it. Which variables will you use to help you get what you're looking for? I made a full video on variables, explaining how variables are got, how do you know the independent one, the dependent one. I made a full video about that, like I told you. You can go to Teacher Hebo William on YouTube. You'll find there practical guide. It is there. You'll be able to see that video. I'm guiding on variables. I made a full video on variables because I realized very many students had challenges on variables. But what are the variables? First of all, these are just measurable quantities. And they can be, here we expect you as a learner or a student to identify for us or to identify for the scorers what the dependent quantities are, the independent quantities, and then the controlled quantities or variables. So, like I told you, I request the one who is typing on the screen, please. The one who is writing on the screen, I see it is Lion of Judah, please. Oh, Lion of Judah. Mr. Kaziva, is it okay you disable for me that? Okay, that's good. Thank you. So we are talking about variables, and I've said that under variables, we expect the learner to be able to identify the dependent, independent, and controlled variables. So some of these quantities may be measurable, whereas others may not be measurable. Examples of measurable quantities can include like the position of the pointer if you're using a meter rule and a spring. It can be angles if you're maybe dealing with plane mirrors, glass blocks. It can be masses. If you're suspending masses, they are measurable. Time, if you're using a stop clock. So these are variables that you can measure. And while others, they may not be measurable. For example, wind. You may not be able to measure the amount of wind in particular, or during the experiment. The amount of light, you may not be able to measure it in an experiment. So some of them may be measurable, while others may not be measurable. When we go to, now let's look at the independent ones. Now here, when the variable or the quantity that you're going to indicate under independent, it should be that quantity that you're going to measure. You, the experimenter, will change. After changing it, then you observe its effect. That is what we call the independent. You change it so that you see what does it cause. For example, masses. You're suspending the mass so that you can see how much extension is it causing. That is what we call the independent. It may be, let's say, length of the constantan wire. You're changing the length so that you see how much current are you now registering after changing the length. So it makes those quantities and others like angle of incidence. You're changing the angle of incidence so that you get the angle of reflection or refraction. So that makes that variable to be independent. So those are what we call the independent variables. So students, please sometimes students, you find they are making a mistake where maybe you find that what they are calling independent is what is actually dependent according to their experiment. You find a learner, for example, is saying angle of reflection is independent and the angle of refraction is dependent. I mean, the angle of reflection being independent, then the angle of incidence being dependent, which is impossible. How will you get the angle of reflection before having the angle of incidence? So you realize that it is the angle of incidence that will give you the angle of reflection. So mind about that. Make sure that what you're calling the independent variable is what you, the learner, changed so that you measure the other quantity. So that is about independent quantities. If we look at dependent, like I've already explained, independent, it means to tell about dependent. These are the ones you will measure after you have changed the other one. The result, when you change the independent, then you measure the dependent. Take an example, the new position of the pointer or the extension. You suspended your mass, which was independent. Then now you're trying to see what is the new position now, or what is now the extension. That means now that is the dependent variable. It may be current and voltage for a given length. You changed the length. You said when the length was maybe 0.1 meters, what was the current? Then you changed it. You said, okay, let me now change the length. You made it maybe 0.2 meters. Then you again seeing what is the current or what is the voltage. So now current and voltage in that case is what we call the dependent variables. Like you hear the word itself, depend, meaning they depend on another quantity. Then we have angles of reflection, etc. So that is about dependent variables. Then under controlled variables, or some other people call them the constant variables. These are basically the variables that you, an experimenter, you don't want them to change as you're doing this experiment. Because if they change, they can cause you to have errors. So those variables, they are the ones we call the controlled. That is why they have the word control, meaning you are controlling them. You don't want them to change. Take an example, like the original position of the pointer. If you're to get accurate results, then you don't want your original position to be changing every time you're going to do the next value. So in that case, we term it as a controlled variable, a controlled quantity. An example, internal resistance of the dry cell. You don't want it to change as you're doing the experiment, or the diameter of the bare wire, because you know, if these change, it means the values you are going to get, they will now start changing. The values will start having errors. So that is controlled, or what we call the constant variables. The smoothness of the reflecting surface, the type of the mirror. Some of them, they may sound weird, but that is because when I say smoothness of a mirror, I'm meaning you don't want to have one point you're having a smooth mirror, another point you're having a rough one. You know that will have an impact on reflection. You don't want at some point to be using a plane mirror, then the next value you're changing, you're putting a concave mirror. Obviously, you'll have a change in results. So that is why it is called a controlled variable, because you will not want to change it. You want it to remain constant. And very many others, like the wind, like the amount of light in the room, all those you don't want them to keep changing, because when they change, they can affect your results. Then when it comes to hypothesis, I don't know who is putting ticks here. It is really disturbing. It is distracting. Okay. So the hypothesis here, the learner, like I had told you earlier, under hypothesis, we expect, or you're expected to give the known facts, or the principle, or the approximate, or the expected findings, and the purpose of that value, the purpose, or what it will mean if you get that exact value. Some of these facts or principles, they may be already known, because maybe previous scientists had determined them, they had carried out experiments and they confirmed them, and so on. A case in point is like acceleration due to gravity. In an experiment, you may be tasked to determine acceleration due to gravity, but you know from previous studies, before even you start doing the experiment yourself, you're already expecting that your value should not be not very far from maybe 9.8 or 10, depending. So you already know. That is now meaning you as a student, as an experimenter in this case, you're going to predict, write the prediction that the acceleration due to gravity might be this, or may be lying in this range. And therefore, what does it mean? Now you link it with the purpose of why you're carrying out that experiment. Suppose you get it in that value, what will it mean to the experiment you are doing? Okay? If it is a spring constant and you are given the approximate value or the expected value, what will it mean? Will it mean that the spring can now be used, or it will not be used? So that is hypothesis, or what hypothesis means. That is hypothesizing. You're trying to predict the outcome. So as a student or a learner or experimenter, you're expected to give your prediction or the hypothesis. Then we look at procedures. Here, under procedures, we expect you to list the apparatus used. This is at least this is something that I expect all learners to score, because the apparatus in most cases, I think the teachers will have always displayed them. And so it is you to name or to list down what you have used in that experiment. It is embarrassing to find that you did the experiment and you failed to identify any apparatus that you used. That is really embarrassing. At least let us try to make sure you identify the apparatuses that you have used during that experiment. Then the student is as well expected to draw a working diagram for the experiment. If you realize, I have underlined that word working diagram. That word, I've underlined it, working diagram, meaning when you look at that diagram, is it true it can give the result? You may find the student has connected, let's say, according to the setup, I'm using an example, someone draws a diagram and shows that the spring was suspended let's say, it was suspended on the meter rule, for example, or the spring was suspended very well, but according to the diagram, the learner is indicating that the masses are suspended on the meter rule. Now, sincerely, do you think that can give you the results? It cannot. So that is what we mean by a working diagram. I think for the diagram to score, it should be working. Like, it should be, even you, when you look at it, it should be able to give the results. Okay? That is about a working diagram. Then after the diagram, you're required to write the steps precisely and coherently. Like, write the steps precisely and coherently, the steps that you followed when you are carrying out this experiment. So those are the ones that maybe you know. Okay, majority of the people think those are the procedures. And they tend to think maybe apparatus, diagram, they are not part of the procedures. They are part of the procedures, because in actual sense, you realize as you're writing the steps that you're writing, you are actually referring to the apparatus and the diagram, the setup. So apparatus, diagram, they are all part of the procedures. I know some people may want to ask at the end, so where are we expected to put them? You can always write them before the steps. Just indicate them before the steps. Write apparatus, then indicate diagram, then start the steps. Okay? You can name them maybe step 1, A, B, C. Others can choose to use 1, 2, 3. Though ABC looks more efficient. That is about procedures, and I had summarized the procedures into this format. I summarized it for my students to help them know. Under the procedures, sometimes students forget. They don't know how do they flow, or how to flow coherently, step by step. It is like if I told you, I know majority are now seated down. If I told you to, let's say, go out, and I tell me the steps that you followed, I know you'll find some other person will say, I opened the door. Then after writing that I opened the door, that person will realize that before he opened the door, he first walked to reach the door. Meaning now you have missed out a step. Okay, you have not flown coherently. And you find maybe after he remembers that, hey, I first walked to the door, then narrates now, I walked to the door. Now you realize it is not flowing well. How do you open the door before reaching there? So that is what we mean by coherence. And I think you can also realize that it matters. And the proper way would be, maybe you stood up, you walked to the door, then you opened the door. That would be the correct steps. So, and that is what we expect. Now, for me to help the students understand or always flow well, I tried to summarize them in this format, whereby procedure, you should have among your procedures, the procedure which refers or explains the arrangement of the apparatus. Then, after arranging the apparatus, I would expect you now to a procedure which may require you to get an initial reading if in that experiment there is an initial reading. Then I would expect, let's say, my learner to give a procedure that guides on how to set the first independent variable, and then how to set the first, or how to get the first dependent variable. Now you realize already by looking at these are so far four areas that I've told you. And if you're writing your procedures, sometimes you can break a certain area into a number of procedures. Let's say an example, that one of arranging apparatus. Another learner may choose to write everything in one procedure, whereas another one may break it into, let's say, 2 or 3. For example, if you're using, let's say, meter rule, spring, retort stand, one may say a spring is suspended on the retort stand. That is his procedure number 1. Procedure number 2 says the meter rule is also clamped on the retort stand. Then procedure number 3, a mass is suspended. You get. So those are 3 procedures which are all talking about arrangement of the apparatus. Whereas another student may just write everything in one procedure, says the spring was is suspended on the retort stand and alongside the meter rule, and then the mass is hung or suspended on the spring. You realize that one has written all the steps in one procedure, but that does not matter. What matters is, have you gotten yourself a procedure that talks about the arrangement of the apparatus? If yes, then you're good to go. Then you go next, initial reading, next, independent, next, dependent, and then you have now the procedure guiding on repeating of the several independent variables, because as a scientist, we don't expect, you are not expected to do just one value and you use that one value to get a conclusion. No. That's not right. As a scientist, you have to take several values. At this level, we encourage you to take at least 5 or 6 values, so that those values, the more values you have, the less the error that you have in your results. You're minimizing the errors, and you're getting closer to the correct value. But if you do only 1 or 2 values, yes, you will have done the experiment, you'll have gotten the results, but those results, there is a high chance that they are wrong because they are very far from the correct value. So we encourage learners to always do repeating, and using several values, so that to have different answers. I see someone raising a hand. Is it Kasuku said? I don't know, Mr. Kazibi, is it okay? We'll be taking hands at this point. Mr. Kaziba, I don't know if you're there. I see also Katkamusi. SDIC Katkam is also raising a hand. Mr. Kaziba? Okay, let us proceed. I think we shall have the question of the session for question and answer at a later stage. So those with the questions, please note them down. Note them down. We shall have them at a later stage. I see Katkamu, I think they have a burning issue. I don't know what is the matter. Katkamu, I think you can.
Mr. Good afternoon.
Good afternoon. How are you?
I'm fine. I'm asking that are we supposed to include the materials in the procedure or we differentiate them?
The apparatus.
Uh,
I had already said that you can list your apparatus just before the procedures, because they are part of the procedures. Is that okay? Good. I see Apak is also having a hand raised. Apak. Apaxid, you can unmute, then you ask if you had a question. You have not unmuted, we can't hear you. Maybe I will request members, in order not to lose a lot of time, allow me go through. I finish at the end. I had prepared. I know we are going to have the questions coming. Just note down the questions, then we shall have them, because now we shall lose time as we are trying to pick questions, and yet we still have a lot of information that we need to share. So let's note down the questions. You're going to ask them during the question and answer session. So let's proceed. I was indicating or showing you the procedures or the steps that you're supposed to have, the important procedures that you're supposed to include in your setup or in your report. Then we have a procedure that you're required to have a procedure that will be guiding on recording of your results, including any other variables if there are any. And then you'll be required to have a procedure guiding on plotting of the graph. St. Andrea SS, please don't write on the screen. Don't annotate. Good. So that is about procedures. Then you'll be required to have a procedure for calculating the task. In other words, a procedure that guides on how you will get what you are looking for. That is what I've called the procedure for calculating the task. Then, now let us, I summarized it into this, I don't know how you'd call it, or acronym or what. I use it as people in deep Russia take good coffee. Now, if you realize what I've summarized here is helping you, the learner, to recall the important procedures that you need in your setup, the important procedures. Like you realize the people, the first one, people. That means, like I told you, that is where you're writing the procedure that is talking about apparatus. Now you may wonder, apparatus starts with A. Why did you use P? Yes, but you hear the word apparatus, P is a dominant letter in the word apparatus. So that's why I chose to use P. So P meaning that your first steps should be talking about the apparatus or the arrangement of the apparatus. Then the first in is for initial value, if any. Some setups, sometimes they require initial values, whereas others, they don't require. Take a case in point, if you're doing, let's say, a spring, but you're using a spring, you'll need to know the initial position of the pointer. Now, that is this procedure where you're talking about how to get the initial position. Or if you're using, let's say, a meter rule balancing on a knife edge, you may need first get the center of gravity, the center of mass for the meter rule. So that is an initial value. Whereas some, they may not have. That is why you see, I've said this in here is sometimes there, is sometimes not there, because some experiments, they don't have initial values. Then the next in is for independent value, the first, where you explain how you are setting the first. Let's say you're saying 100 grams is suspended on the spring. Now you're describing how you're setting your first independent variable. Then with the corresponding dependent variable, that is D, for deep. Then Russia, that is repeating values. Now here you're writing the procedure where you're saying procedure this to this are repeated for values of, let's say, AM, or for values of X, for values of LO, for values of this, being this dash, 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 okay? That is now for repeating. Then take, that is for table of results. The procedure which talks about writing your table of results. Good is for graph. The procedure which talks about the graph. Which graph are you going to plot and why are you plotting it? Because in some experiments you may find you are plotting a graph so that you get it slow. In some other experiments you might find you're plotting a graph so that you get its intercept. So in that procedure, that is where you say a graph of this against this is plotted and the slope S determined, and the intercept on this axis is determined. That is about the graph. Some other people, they may decide to break it into two procedures. That procedure about the graph. One may say a graph of this against this is plotted as one procedure. Goes to the next procedure, says the slope S of the graph is calculated or determined. Or says the intercept C is determined on dash dash axis. So that is about good or about the procedure for graph. Then coffee, that is for calculation and conclusion. Now, this is where you write the procedure which is guiding on how you'll get what you're looking for. If you are in this experiment, you're looking for force constant K. Then now in that procedure is where you're writing the force constant K is then calculated from, then you show the expression. Or you're saying the acceleration due to gravity is calculated from, you see, that is the procedure for like, which is literally supposed to be the last procedure. I'm sure if you followed this order, like I said, some of them can be broken into many sub procedures. But my whole idea is to guide you on the important points that you're supposed to take note of as you're writing your procedures. Remember, coherence matters, and I think it also attracts some scores. So that is the procedures or the steps, how we write the steps. Remember I said that under procedures, you'll write the tools you have used or the apparatus. You draw the diagram, but that diagram should be working. When someone looks at it and connects, following it, it should give results. And then you give the steps that are followed or that you followed when you are carrying out the investigation. And I've summarized for you the steps. If you don't want to forget, always remember, people in deep Russia take good coffee. That will always remind you the steps you need to write down so that you don't black out, you don't forget. Or sometimes I see my students when they are doing the practical, you see someone scratching the head, doesn't know what is the next step to write. But if you recall this, then you'll be able to remember which step am I supposed to be following next, okay? Let's look at the errors and the precautions, or what we call the risks and remedies. Remember, like I told you, here the errors you're stating at least two possible causes of inaccuracy. When you are carrying out this practical, what are the most likely issues that could have caused you not to get correct results, or things that threaten the correctness of your results? So that those are the ones that we call the sources of errors or the sources of inaccuracy. And then you have to also give the mitigations. It's like you're now, as a scientist, you're guiding. As a scientist, you're guiding other scientists who may look at your report that if you're going to follow this experiment, please be careful. This and this can cause you problems. This and this can cause you to get not correct results. And go on and tell that person how to mitigate them, what can be done, or even you're telling how you mitigated those problems, how you prevented them, okay? That is the sources of errors and precautions. Then we look at presentation of data. Now, like I said, you are expected to present your data in two ways. One is you can record your data outside the table of results, if there is any, and then the majority of the results are supposed to be in the table of results. And like I said, that table of results should be in a column form. I know they may tell you even in raw form is okay, but as a scientist, it is better to have that table in a column form, okay? It is easier for you to observe and analyze clearly and even observe the trend. So the ones outside the table of results, of course, those are the ones we had talked about, the initial values. You might find maybe you needed to get P naught, initial position of the pointer. You might find you needed to determine maybe the EMF of the dry cell first. You might find maybe you needed to determine the, let's say, the balance point of the meter rule when it is unloaded. So those are the values, kind of recordings that you write outside the table. Whereas these other ones you're carrying out, the independent and dependent ones, those are the ones that you write in the table of results. Then let's look at now the table of results. What is it expected to have? under table of results as you're doing the table of results. One, that table of results should be well drawn and closed. Students, please don't leave your table of results open. You find you have not drawn the table, you're using just the margins in the book. That is not proper. You're leaving your table open. Please draw the table. Show someone that the table is drawn. The horizontal lines, I know people may want to ask, how about horizontal lines? Do we need to have them? So the horizontal lines, you may not need to have them since they are clear, but vertical columns, draw vertical columns and close it very well. And you need the row for labels up there where you're labeling. It will be proper when you also draw it clearly, you indicate it is that row. So I know some of these things may sound like they may have told you that they don't matter, they don't do this and that. It is true, some of them, they may not be causing any impact on your scores, but it is important as a scientist to be organized and to be neat, okay? It's important. So that when we are telling you, that is why you realize I'm using the language better. It is better to do it this way. It is better to do it the other way. Then you expected, excuse me, you expected, of course, like I said, your table should be columnar. In other words, it should be having columns. That table, it should have variables well indicated in the header row with their units if they have. For example, if it is mass, should be indicated with its unit, kilogram, in brackets. If it is length in meters, in brackets, if you decided to use meters or centimeters in brackets. If it is angle, degrees in brackets. So that is what we expect to have on the table of results. And of course, in the table of results, we expect you to have your values recorded following a particular trend. They should either be increasing downwards or reducing. You see that? We don't expect, or you cannot, as a scientist, you cannot carry out an experiment which is following a particular theory or a particular formula, and then you find that the values are mixed up. They're increasing, decreasing, increasing, decreasing, increasing, decreasing. No, that is not expected of you. With the values that you're going to record in your table, they should either be increasing or decreasing depending on the experiment. So that is what we call the trend, okay? Then the values, of course, they're expected to have correct accuracy. Now, accuracy is another different idea that can take us a full lesson to talk about. Because how you manipulate depends on the rules you're following. Because when you're adding, you follow certain rules. When you're subtracting, you follow certain rules. When you're multiplying, dividing, reciprocal, squaring, that is not the accuracy I'm talking about. If you're going to carry out a certain manipulation, then the value should be written with correct accuracy, of course, respecting the rules of data manipulation. That is about recording of data, what is expected of you. Don't mind, we are going to look at a sample scenario and we see how it looks like OH is worked out. Then we have now data analysis and interpretation. Now, data analysis and interpretation, here you're going to analyze either using a graph or calculation like we saw. Now, your graph, of course, we expect your graph to have some of the things you may already be knowing them. One, should have a title. Never forget your title. Two, it should have the axis labeled with either units if the label has a unit or not. First of all, you draw the axis. It should have an arrow. That axis should have a label. What axis is it? Is it L? Is it M? Is it extension? Is it current? So if it is I, you label it I. If it is V, you label it V. If it is R, you label it R. Okay? That is what we call labeling. And you give its unit in brackets. Avoid issues of double labeling the axis. You find you have put an axis of I, you have gone ahead again up there, you have written Y-axis. That is not proper. Now, which axis should we take? If you look at it now, you've called it Y, you've called it again let's say I. Now, which one should we take? It's like someone calling you, let's say your name is, let's say Moses, and then again another person gives you another name, Mary. Now, Moses and Mary, which one is your name? So it is not good to double label the axis. Then it should have a uniform scale. Your graph should have a uniform scale. The teacher should have already told you about what uniform scales are, or what we mean by uniform scales. Maybe to give you a hint is if you're moving in steps of 1, 1, 1, let it maintain 1. If the value is 10, the next value is 11, the next value is 12, the next value is 13. You're following that uniform. That is the uniformity. If it is 2, 2, 2, you maintain 2, 2, 2. If the first value is 2, the next one is 4, the next one is 6, 8, 10, like that. That is what we call uniformity. Don't make mistakes of your rating. The first value is 2, the next value is 4, the next value you rate 5, the next value you rate 7. That is not proper. You realize you'll have disobeyed the uniformity you have changed. So ensure that your scales are uniform. You should have correct plotting. Should have correct plotting in the graph. Maybe the teacher could have talked about that already. And you should have the line of the best fit of your graph that will help you to get slope. And of course, when you're getting slope, you're expected to indicate the method that you have used. Indicating, we mean maybe you're drawing a triangle, or some other people extrapolate on both axes. Some other people mark the coordinates. When they have indicated the coordinates that they have picked, whichever method you're using, ensure that you have indicated the method of finding the slope. In other words, me as a teacher, I can be able to see in your work, I look at your graph and I be able to see, okay, this is where he or she is reading his or her coordinates for the slope from. So that is the purpose. Then for calculations, that is now again, because after having your graph, of course, you'll be now calculating. The calculation can be calculating the slope. It can be trying to calculate the unknown you're looking for using a given expression. That is calculation. Now, what do we expect in calculation? One is correct formula and correct substitution. You have to do them correctly. Then you have to do correct arithmetic. What I mean by correct formula and correct substitution here, some people may not understand what I mean. For example, when I say you have plotted a graph of V against I, that is voltage against current. Meaning if you're going to get slope, expect your slope to be change in V over change in I. Because V is on the vertical axis, I is in the horizontal axis. Now, some other people may find they are interchanging. They are saying change in I over change in V. You realize now that is now formula. You're spoiling the formula. Then substitution, you may find instead of having, many of you are used to Y2 minus Y1 out of X2 minus X1. You find someone, when they are bringing in the coordinate for Y2, he has put it in position of Y1. That is now wrong substitution, okay? Or you are going to substitute, you're getting an expression, you're getting, let's say G is equal, let's say 4 pi squared S, an example, 4 pi squared S. Then you find a person, in his calculation, the slope was 2. But in substituting here, rates in 1.5 as S. So that is now wrong substitution. Then arithmetic, that is the normal calculations. Of course, respecting the rules of data manipulation. I said that is now another idea that we may have to share some other time, or the teachers may share them with you, data manipulation. Which rules do we follow when we are subtracting, when we are multiplying, when we are dividing? That is what we mean here. That is under arithmetic. Also, you find some other people, they are adding 100 plus 5. The person rates 150. That is wrong arithmetic. You're supposed to add properly. It was 100, adding there 5. But the answer here, the person is indicating 150. Yet you added just a 5. So that is wrong arithmetic. So that's what we expect you to do under calculation. Then, of course, your value should as well be correct. If it was, for example, if it was, let's say, acceleration due to gravity, obviously here on Earth, we cannot expect acceleration due to gravity that is 40 meters per square second. That is impossible. So, but if you find now, you carried out your calculation, everything, but the acceleration due to gravity is 30, then obviously that value will not be correct, and I think it will not score. So, of course, under calculation, the value is expected to be correct. Then the correct unit as well, you cannot say you were calculating, let's say, let me say you're calculating acceleration due to gravity, and then you tell me that its unit is degrees. That will not be correct. So the unit of the quantity you're calculating is also expected to be correct. That is about data analysis and interpretation. When it comes to conclusion and advice, here you're trying to link, the learner is expected to link the answer or the value you got with the hypothesis, and then you give the advice. Remember, in the hypothesis, like I told you earlier, you had already predicted what the outcome is, or they may have already told you, given you the values that maybe you expected to get. Now, if you carried out your practical, what is the relationship between what you got and what you expected to get? That is now under conclusion. Then, if you see, when you look at that value, what does it mean from what you're trying to solve in this problem? What does it mean? Does it help you solve the problem? If it was a spring constant, and they told you the force constant was lying between a given value, and for you, the value you have got is not in that required value, will you now be able to use it? Will you not be able to use that spring? No. Now you realize you're going to form to give an advice basing on what you have got. That is for conclusion and advice. So I want to first, now I want to take it to the sample item, but I don't know if Mr. Kazibi is back. If I go to the sample item, maybe I take in some few questions, then I proceed. Is it okay, Mr. Kazibi? Are you there?
Yes, Mr. Hub. Yes, it's very fine. We can take on only 3 questions.
Okay.
The first one we can take on from Light Vocation Secondary School. Unmute.
Thank you so much, sir, for the presentation. What I would like to ask is that in which tense would be suitable for us to report the procedures? And like as you've said that we include the apparatus in the procedures, but I'd like more clarity on whether I can write them separately and give their purpose of each. Thank you.
Okay, thank you. About the, you asked the tense, the suitable one would be present continuous because you're reporting what is being done. But since this is not English, we don't focus so much, but like I'm saying, suitable one is present continuous, where you're saying statement like, the spring is suspended on the retort stand. The mass is suspended. You realize the language. It is continuous, present continuous. However, even if you report in the past, because you're reporting what you did, the spring was suspended. This was done like this. So it doesn't matter. So that is about the tense. Then the apparatus, like I said, well, I don't know why students are really having issues with that part. I said, when you reach procedures, just indicate apparatus, then list them, the ones you're going to use. After them, draw diagram or setup. Draw your diagram. After them, indicate steps. Okay? Then you write. It's simple as that. No big logic. Even when you don't indicate them, even when you don't indicate apparatus, diagram, what, I believe the teacher can be able to see that these are apparatus, these are, but of course for proper reporting, it's important for you to indicate the materials you used, that these are where the materials I used, this is how I arranged them, that is the diagram, and this is how I carried out the experiment. That is the 3 things that are under procedures. Yes, Mr. Kaziba, another one?
Okay, Safe Haven Christian School.
So good afternoon, teacher. So my question is under the variables. Imagine that if a student have just written variable, then he or she has given, like for example, if I'm carrying out my experiment to determine the refractive index, so then the student just write the variables without separating them because sometimes it's very difficult to separate the independent variables than those dependent. Then that's the student has given angle of incidence, angle of refraction, then light intensity under the variable. Will the student be marked wrong?
Mr. Kaziba.
Yes, sir.
Sorry, someone called me and disconnected my Wi-Fi. If it is okay, please rewind for me the question. I did not hear that next question.
The gentleman was asking whether it is okay not to separate the variables, the independent, the DV, more so now when it comes to light experiments.
Whether it is okay to do what?
Not to separate.
Like what? Like
in light, you mentioned something like in case when it comes to light, it may be hard for someone to distinguish, maybe like to separate, like these are independent variables, these are dependent variables, these are intervening variables, something like that. Whether it is okay.
Separate them. To not to separate.
Yes.
It is very important when you separate. It is very because we want to know as an investigator. Remember here, you're doing as an investigator, you're carrying out this apparatus, but you're also guiding. It's like the report you're making, you're guiding another person. If he or she can carry out that same apparatus. So you're telling that person which values can be used as independent, which ones that person can change to get the other. So there is no, you can leave them there hanging. I know somewhere, somehow you may have a score, but you'll miss another score somewhere for not separating them. So when you're confused, it is okay. You can have them there. Well, they are variables, but still separating them is really needed. It is needed. Next question.
Yes, then the last one, CATCAM SDA. CATCAM.
Mister.
Yes, sir.
How many decimal places do you consider during our practical?
For how many decimal places?
Yes.
During the practical?
Yes.
Okay. So that's all you wanted to know. You have another?
That's all.
Okay. So for decimal places or significant figures are determined by the apparatus you're using. Take an example. If you're using a meter rule and you're rating values from a meter rule in centimeters, then you know that a meter rule cannot go beyond 1 dp. So the values that you'll get from a meter rule should be to 1 dp. If you're using, for example, a stopwatch gives values to 2 dps. So the values for a stopwatch will be written to 2 dps. If you're using a meter rule, but you're rating values from a meter rule in meters, then they are now you're manipulating because the meter rule was giving you centimeter, then now you're changing it to meters. The rule of data manipulation coming, though you know it will be 3 dps. So significant figures or decimal places are determined or they are dictated by the apparatus you're using. You always look at the smallest value on that equipment. That is the simple method. Look at the apparatus you're handling. The smallest value there, the smallest thing it can measure, the smallest division, what is its value? And that value has how many dps? Those are the dps you should write for that apparatus. So that is about, we don't have predefined that in an experiment, you are supposed to use these DPs or these. No, it is the apparatus you're using that dictates for you the DPs you're supposed to use. I hope I answered you well. So, Mr. Kazib, I think I can proceed.
Let's proceed. The rest,
All
please,
right.
let's have the questions in the chat. Let's have the questions in the chat.
So, okay. Now I want to show you. I want to show you there is some background noise. I'll beg they mute. Good. So there is a, here I have a sample item or a sample scenario. A group of farmers in the village have food items which they always share in equal proportions using a spring balance, whose spring is of force constant ranging between 45 newtons per meter, 50 newtons per meter. One of the farmers damaged the spring balance, and unfortunately, they were unable to repair it. So that is a scenario now. The problem at hand. People, they've been using their spring balance. One of the farmers damaged the spring which is in that spring balance, meaning the spring balance is no longer working. But one thing that is known, that spring has a force constant between this range. See? So they are now asking, the task is now, as a learner of physics, advise the farmers whether they can use the spring in the school lab to replace the damaged one in the spring balance. Now you realize here the question, they are not telling you what you're supposed to look for, but they're asking you advice. Can the spring you have in your lab be used to replace the damaged one? See that? Now you as a student, as an investigator, here you quickly get to know. It quickly comes to your mind, if now I'm going to advise them, it means what are the conditions, the terms and conditions for this spring? First of all, you know, it must be of force constant around here. Now the next question comes, do I know the force constant of the spring which is in the lab? Obviously, the answer would be no. Now, the next question is, how can I get it? That is all investigation. You're starting to investigate. Scientific process. You're starting to do an investigation now. Now, meaning the next, you realize that for you to give advice, then you need to carry out an experiment where you'll have to determine the force constant of that spring. See that? So that is how you should, first of all, interpret the scenario, look at the task, and get to know what you actually need. What they needed you to advise, but you realized you cannot advise without solid information. So now when we look at our aim, I know majority now they already know what will be the aim of our experiment. The aim of the experiment will be what? I know you already must be mentioning it, an experiment to determine the force constant of the spring provided. And why are you determining that? Remember what I told you about the aim? That you give what you're looking for and why you're looking for it. So we have said in this experiment, we shall be determining the force constant. Why shall we be looking for it? We want to see if it can replace the damaged one. So those are the two parts. And that is how you'd state the aim of the experiment in that case. Next would be the variables, for example. Sometimes people here ask, does the order here may not matter, like about between variables and then hypothesis, it may not matter. But let's look at variables. What will be your independent variables? Now, this is where unfortunately, I would have shared with you the video that I told you about the YouTube. It plays a big role here. Remember, I told you about variables. I have that full video there. Now, you realize for you to know the variables, you need to first of all know, is there any theory about what I'm looking for? If I'm looking for force constant, is there a theory about it that I remember any formula in theory? You realize, yes, Hooke's law. And Hooke's law, what does it say? Force directly proportional to the extension. That is Hooke's law. Unfortunately, I could not type it here, but I'd have shown you. Now you realize, let me see if I can try using this. So if the theory is force is equal to, is directly proportional to extension, is Ke. But we realize in this, in the lab, do we have force? No. What we have is masses. Now, how can I change force into mass? We know if we get mass, we multiply it with acceleration due to gravity, then we shall have our force, or which we call the weight. So the equation, I request Icon College, please don't annotate on the board. So you realize that I have changed my force into mass, because those are the ones I have in the lab. Now you realize between these, I see acceleration due to gravity is what I'm looking for. No, it's not what I'm looking for. I'm looking for K. That is a force constant. But acceleration due to gravity is known. That is a constant. It will not change throughout the experiment. Meaning the only things that I can change is the mass and the extension. Now it is upon you now to determine between mass and extension, which one can you easily change so that it gives you the other. You realize?
Teacher,
Yes,
now,
please.
now go on your screen. On your screen, there are some three dots on the upper right corner. Where do you see those green things where you're picking the annotation pen?
Yes.
Yes, then click on those three dots.
Yes.
Then there is something, disable annotation for others.
Oh, yeah. Okay, I have. Is that okay? Yeah, good. So I was saying now, remember this part of variables, it requires now someone to now be a bit focused, because you'll need to know which one will be independent variable, which one will be dependent, and how will I get what I'm looking for. Now you realize if I have changed my force into mass and the acceleration due to gravity, I've said the acceleration due to gravity is known and it will not change throughout the whole experiment. So you realize you have mass and the extension, the ones you can change. Now you realize that the only between mass and extension, the one that you can change, you, the person doing the experiment, the one that you can change is mass. When you change the mass, you'll be able to determine the extension. So in that case, your mass now becomes the independent variable. Then it means now automatically when you change the mass, it gives you'll be able to measure extension, meaning now extension will now become the dependent variable. Now, remember how you get the extension? You can either get it using the new position of the pointer and so on there. So you can use the new position of the pointer, you subtract off the initial position, then you get your extension. So that will be now the dependent variable. You realize how we got to know the independent and dependent. You first looked at what you're looking for. You saw between them which ones you can change and which one you can measure when you change the other. Then you identify the independent and the dependent. Then the controlled variables, these are the things that we don't want to change. An example is the initial position of the pointer. We don't want it to change as we are doing this experiment. The mass of the spring. When we say the mass of the spring, we are indirectly meaning you cannot start using one spring, the first value, then in the next value, you bring another spring. No. Because changing its mass means you're changing its force constant. So that will cause you problems. So that is why it is a controlled variable. That is about now variables, independent, dependent, and controlled variables for our item that we are looking at. After now looking at them, next is we are supposed to look at the hypothesis. Remember in the scenario, let me first clear this. Cool. In the scenario, remember they had given us that in the scenario they had given us that the spring constant of that spring which was spoiled was between 45 and 50 newtons per meter. And that was in the scenario. Meaning even us, before even we start doing, we expect or we predict the spring constant for our spring might be in that range. So we shall state our hypothesis as the spring constant lies in the range 45, 60, sorry. The other in the scenario we had used 50, sorry about this. Here I made a mistake in typing, I wrote 60. But we can take it. The good thing, you get the idea. We are picking the value from what is given in the scenario. So it is for between 45 and 60, and therefore what will it mean to us? If we get our value in that range, it will mean that the spring we have can be used to replace the damaged one. That is the two parts that I told you, even under hypothesis. We are saying what we are predicting to get and what it might mean, or the decision it can lead to. So that's why here we're predicting where it might lie and the purpose of what we expect to use it for. Then we go to the procedures. Like I told you, under procedures, I'm just going to look at, we shall have our apparatus, and the apparatus include the retort stand with a clamp, the spring with a pointer, 600 grams slotted masses, meter rule, etc. If you have others add piece of thread, etc. But at least me, I've identified the major apparatus that I need to do this experiment. Then I have my diagram. I can have my diagram looking like that. So you see, this is what I was telling you, a working diagram. The diagram, so I'm having a retort stand. The spring is on the retort stand. The mass is on the spring. The pointer is facing the meter rule. See that? That is what we call a working diagram. Like I told you, you may find another person has decided to bring a mass from here, from the spring, is showing that it is suspended on the meter rule. Really, that cannot give you the results you expect to get. So that is what we mean by a working diagram. Then now I will go to the steps. And under steps, the first procedure, like I told you, remember our rule? If I can remind you, people in deep Russia take good coffee. Meaning the first being apparatus, the procedure for apparatus. Now that is why you see my procedure here is talking about the apparatus. The spring is suspended on the clamp alongside the meter rule. I'm talking about my apparatus, how I'm arranging them. Another person, like I told you, can decide to subdivide this, says the spring is suspended on the clamp. The meter rule is suspended alongside. The pointer is fixed on the spring. You see, you're braking, but remember, the more you brake, the more time you're going to take. So you might not be able to finish. You'll be eating your own time. So when you try to write your procedures precisely, but with the same meaning, carrying the meaning, then you'll be safer. Then the next procedure is supposed to be in, and we said in is for initial value, if there is any. Now, since this practical is about a spring, then our initial value we expect to have it. That is the initial position of the pointer. So the initial position of the pointer, my next procedure is the initial position of the pointer, P naught, is read and recorded. See that? Now I've talked about the initial position. Now, according to my steps, the next step is supposed to be what? Remember we said people in, deep. In, the first in is for initial, if it exists. Then the next in is for independent variable. I'm going to write the procedure where I'm directing or I'm guiding on how to set the first independent variable. So you'll say the mass M of 0.1 kilogram, that might be the same as 100 grams. No, don't come. That might be 100 grams. So you're saying the mass M of 0.1 kilogram is hung on the spring, or another person can say it's suspended on the spring. Then that is now the second in. You realize I've said people in. The first was for apparatus, next was for initial value, next is now for the first independent variable. Now I'm going to go to deep, which is now for dependent. How will I get the dependent variable? I've set my first independent, which is the mass. Now, how will I get the dependent? Remember the dependent, I said the extension. Now, I realize for me to get the dependent, I will need, first of all, know the new position of the pointer. So when I suspend the mass, I will determine now the new position of the pointer is determined or is read and recorded. But remember, P1 was not my dependent. For some other person may use it as a dependent, P1 directly, but me, I'm choosing to use not to use it. I want to use extension itself. So after even I have stated that, I have not yet gotten my dependent. So I will add on, how will I get my dependent? Now I'm saying the extension E is calculated from new position of the pointer minus original position. Of course, you know, when you suspend the mass, the spring will stretch. The value will not be new. It will be bigger than where it was. So you'll be able to get the extension E. Now that is how the procedure. Remember here, a student may choose to write this in two or three procedures. May say the new position of the pointer P1 is read and recorded. Writes another procedure. The extension E is calculated from P1 minus P0. Decides to write them in two procedures. The whole idea is the procedures you're writing should be able to guide or should be guiding on how you can get the dependent variable. Then we have, now you go from deep, we are going to Russia. Now, when we're going to Russia, that is repeating procedures. Now I'm going to see which procedures do I need to repeat to get several values. Because I'm going to repeat procedures where I'm setting independent values or variables up to where I'm able to get my dependent variables. Those are the procedures you're supposed to repeat. You repeat the procedure starting from where you set your first independent variable up to the procedure where you're getting your dependent variable or variables. So if I had, let's say, procedure in procedure 8, where maybe I had the independent, and procedure D is where I had my dependent, then I would say procedures A to D are repeated. But since here, my first independent is in procedure C, and the dependent is in procedure D, then I will just say procedures C to D are repeated for values of mass. Now you indicate, you show how the values of the independent are changing. If here I had 0.1, now here I'm adding, I'm increasing 0.2, 0.3, 0.4, 0.5, 0.6. Okay, that is how I'm writing the procedure, which was under Russia, or repeating procedures, repeating values. Then the next procedure now would be what? You can even guess from people in deep Russia. Take good coffee. The next procedure is for take, which is now table of results. So our next procedure would be now the results are recorded in a suitable table. Suppose in this scenario, let's say it was an example, it was, let's say, for a glass block, where you may find for a glass block, I was setting the angle of incidence and then getting the corresponding angle of refraction. But what I'm going to plot is sin I against sin R. So at this point, this is where I add in those values that I did not determine earlier. So I would say now the results are recorded in a suitable table, including values of sin I and sin R. That is where I would include them now under this procedure. So that's why I said this is where you write, you read the guide on how to write, on which values are going to be recorded in the table of results, including those other variables if they do exist. Then after take, we go to good coffee. So good is for graph, meaning now I will have to state which procedure is for graph. What am I going to plot? Now, maybe here you allow me again, try to show you from our expression that we had. Remember we had M G equal to K E. This was the value, this was the equation I had earlier. Now, I need to make sure that at this point, before you go to plotting, before you conclude on what you're going to plot, you need to have your equation should be at least in the format Y is equal to M X plus C. Your equation should at least be in that format, Y equal to MX plus C. Now, but this equation I see it is mixed up. So I can rearrange it and I say it will be M. I'm dividing here by G, which will be M is equal to K out of G, E. So I realize this M is in position for Y, mass is in position for Y, K over G is in position for M, X is in position for E. So it means now I can know if this was an equation of a straight line, if this graph is to give me a straight line, then when I plot M on vertical axis, I put E on the horizontal axis, then I can have my equation, I can have my graph that will be able to give me the constant. And we realize that the constant K out of G is in the position for slope, meaning I will be now able to get, let me first leave it there. So one thing about the graph, we have now seen that I'm going to plot the mass against the extension. So that is how I'll write my graph as a graph of M against E is plotted. And why am I plotting it? I need to get the slope. That is why I'm adding here. I remind you once again, remember, some other people may choose to write this in two procedures. May say procedure, this is a graph of M against E is plotted. Writes another procedure, the slope S of the graph is determined. It is okay, no crime. Me, I prefer doing it this way because I'm trying to minimize space and maybe save time and not to write very many procedures that will maybe confuse me. So that is how I'm writing the procedure for graph. And from our people in deep Rohingya, deep Russia, take good coffee. Now we are remaining with the word for coffee. And that coffee, that is now the calculation or how you're going to get the constant. Now remember in the experiment, your problem was you wanted to get K. How will you get it? Now I'm writing from here, we realize the position for slope, we are having there K over G, meaning K over G, K over G is equal to slope because it is in the position for slope. Now, if it is in the position for slope, me, I'm interested in K. And slope, I'll have determined it from the graph. So how can I get K? Realize I just need to cross multiply. I multiply this side by G. I multiply the other side by G. And I'll have K, which is equal to, if you multiply both sides by G, K will be equal to G S. So that is for how you are going to get your K. You realize that you'll get K from when you get the slope multiplied by acceleration due to gravity. And that now guides me on my procedure for calculation. So I'll say the spring constant K is calculated from K is equal to GS. That is how you can write the procedures for such an experiment. If we proceed to now the results, now these are the sample results that we may have gotten. Or maybe before the sample results, we can have a look at the sources of errors or the risks and then their precautions. Common sources of errors, obviously, one that we can always get to know is that parallax errors in reading. Now, when you say a parallax error, don't just say parallax error. You have to explain where are you having a parallax error. It is maybe in reading the meter rule or in reading the position of the pointer, in reading the protractor, because in most times we use apparatus that have scales. There is a high chance that you can misread the pointer, the position on the scale, and that is what we call the parallax error. So, but you have to be specific because when you just say parallax error, you have to tell where are you having a parallax error. And here we see in reading the position of the pointer may be pointing in 55 for you because you're looking from a different angle, you see as if it is 57, and that can cause the error, and that error is now what we're calling the parallax error. Then it can also be reading the position of the pointer from the wrong scale. Remember, when you have a meter rule is suspended, it is having two scales. One is increasing downwards Another one is reducing as you move downwards. So some other students may make that mistake. And as they are taking readings, they read from a scale which is reducing instead of reading from a scale which is increasing downwards. So that is why it becomes another source of error. Let's say adjusting the meter rule midway the experiment. It means if you have started suspending masses and your reading position of the pointer, it is not good for you to again start moving the meter rule. Because when you move it, it means you are affecting the initial position of the pointer. If the pointer was at 10, now you have adjusted your meter rule, the pointer will no longer go back to 10. If you remove the masses, the pointer you may find is now maybe at 12 or maybe at 8. And that is now a source of error. So it is another source of error. Then also allowing suspended masses to touch either the retort stand or the meter rule, or allowing them to keep oscillating. Automatically, it means it will affect the new position of the pointer. Because if they are touching the meter rule, they will not stretch the spring fully. So that affects the extension you're going to get. So it is another source of error. Then the precautions you have to take, basically, you have to explain or to describe how one can avoid those errors. And it is obvious, it is just being negative of what you have already written. So you have just to state, like if it is a parallax error, then what do? Position your eye perpendicular to the point where the reading is taken from to avoid the parallax error. Because parallax error is brought by taking readings from different angles, from an angle and not perpendicular. Then a mitigation for a scale is to ensure that you read from the correct scale of the meter rule. In other words, the scale that increases downwards. Then for the meter rule, make sure once you have started the experiment, you say leave the meter rule in its original position once the experiment starts. Because here you're trying to avoid affecting the initial position of the pointer. Then maybe the masses, ensure that the masses are hanging freely and they are not oscillating or they are not swinging, bouncing, so that you have an accurate position, new position of the pointer. Those are the precautions. Remember I said you can even give at least 2 whenever you identify at least two errors, and then also identify their precautions. Then you're good to go. Now, when it comes now to results, remember in our steps, we had the first procedure, which was for apparatus. The next one was for initial position of the pointer. So, of course, if I suspended my spring, I'm assuming this was my initial position. P naught was maybe 60. I went ahead to convert it to meters, which will be 3 dp, 0.600 meters. Then I'll have my new position. Remember the next procedure where I said I suspend 100 gram or 0.1 kilogram. I read and record the new position of pointer P1. I've recorded it. It was this. Then the next procedure for dependent was determining extension, and the formula was given. So I have determined it where I've said P1, which is 0.62, and P naught was 0.60. I've subtracted, and the answer is that. So the next procedure, of course, was for repeating. And since I'm repeating, I cannot keep writing values here outside. So I need to have the table of results. Now I want to highlight, I want you to take note that this thing is, let me first make this clear. So I want to make it clear that it may not be necessary, because most of these values like P1 and extension, they are going to come in the table of results. So there is no need of, it is not a must that you must always first write them here since they are already appearing in here. But take a note, P note, you must record it outside, because remember for it is not going to appear in the table of results. So it is a must, it should be appearing somewhere. This applies for an item where you're having initial values like P naught here. So my table of results, now I have shown you, this is how it should look. have here your row, which is indicating the values, indicating the variables, mass in kilograms, P1 in meters, extension in meters. When mass was 0.1, P1 maybe was 0.62, and therefore the extension it gave was this. You're calculating now. M was this, P1 was this, extension was that. So you have finished getting your values. Then now it means you have finished presenting your data. That is data presentation or recording of data. The accuracy bit, of course, is in here. Like when you look at the extension, you got it by manipulating. This is subtraction. The rules of data manipulation apply. I will not go deep into them now. Maybe we shall have some other session where we shall talk about that. But at least you should be having an idea how to manipulate here, how to get these values. The DPs you're supposed to write here. Then now we go to our data analysis. And we said we analyze data in two ways, by graph or by calculation. So I said my graph should have a title, so which is a graph of mass against extension. And I don't know, it may not be so clear. Sorry about that. Be patient with me here. I have nothing to do. The screens may be small, but this is an example of my graph. I have a graph of M against E. I said that graph should have the axis which is drawn. You see my axis is drawn and it has an arrow. It is also the horizontal one is drawn. It has an arrow. The axis should be labeled. It is this axis is for mass in kilograms, and this one down is for extension, which is in meters. The scales should be uniform. Here I used 0.1 as a scale. Here it is 0, 0.1, 0.2, 0.3, 0.4. It is uniform. Even here down, I used the scale of 0.02. Here it is 0, 0.02, 0.04, 0.06, 0.08, up to the last value. So my scale is uniform. And I have gone ahead to plot the values. If you recall the table of result, I can bring it back. Table of result, I say I will sample just 3 values or 2. The first value, mass is 0.1, extension is 0.02. So I come here and I see my mass is 0.1, my extension is 0.02. I plot it. The next one, mass was 0.02 and extension was 0.04. I have also plotted it. So I have plotted all values using a dot and a circle, small dots with a circle. You can even plot using X. You can plot using a cross, but they should be small, okay? With circles, okay? Make them small so that they are visible. We tend to put circles so that we can easily observe. We can easily see where the plots are. Then after plotting my graph, I have chosen the line of the best fit. Don't worry. This was just a dummy. It's something that just for test, for reference purposes. So you may see it is in a straight line, and for you, when you do the experiment, you don't get values like this, then you think you're wrong. No, because of errors that we make, it is very difficult to have all your values here in a straight line. They are just close. So it is you to observe and see that the line you're going to draw passes at least through most of them, or it balances all of them. What remains on the right is equal to what remains on the left, or almost equal to what remains on the left. So remember I said you should plot correctly. I have plotted. You should draw the line of the best fit. I have drawn. And you should have the method for slope. You see, I have indicated here my big triangle. And this side I've indicated it. This side is for change in M, whereas here down is for change in extension, change in E. So that is my graph. Now I'm going to analyze. Now I have already analyzed. I need now to continue analyzing by calculation. This graph, why did I plot it? I plotted it to get the slope. Why do I need the slope? We realize that you need the slope because K over G is equal to slope. So meaning I can get K using that slope if I get it from here. So we are going to continue now to calculation. Of course, I need to determine from the graph, my slope will be changing M because M is on vertical axis, X is on horizontal axis. And if I take you back, we want to see if these are the values for changing M. What was the value here? This value here is 0.7, whereas here the one down here is 0.05. Those are the two values for M, 0.7 and 0.05. So I'm saying 0.7 minus 0.05. I want to comment here. Why have I used 2 dPs? Remember my graph on that axis. If you realize every small line, this graph is now like a measuring instrument. And I told you, for you to know dPs of a measuring instrument, look at the smallest thing on it, the smallest division. Now, when you look at this from 0 to 0.1, there are 10 divisions, meaning each one is 0.01. Now, when you look at 0.01, that has 2 dPs. That it means every value I'm going to read on this axis, I should rate it to 2 dPs. While when I look at the horizontal one, between 0 and 0.02, there are 10 divisions, meaning each small value, each small division is this value here divided by 10, which will be 0.002. That means each one has 3 dPs. So it means every value I'm going to read from this horizontal axis will have 3 dPs. So that is why you see that here, vertically, I used 2 dPs. Well, here I wrote 2 dPs because I realized the last value is just a 0. It was not affecting my calculation so much, but it had an impact. It has an impact. In an impact, you should follow it very well. So that is my slope. Because if I check horizontally, the two values of this value here is 0.14 and the value here is 0.01. 0.01 when you read it carefully. So that gives me my values for the slope. Up it was that, down it is 0.14 minus 0.01. So when I solve, I continue on getting the expression and my slope is that. Remember what was the unit? On the vertical axis, I had there kilogram, which was for mass. And on the horizontal axis, I had there extension. Sorry, I used here X. It is supposed to be changing E. Sorry about this. It is supposed to be E, which was extension. So its unit is supposed to be meters. So it was kilogram per meter. That is for my slope. Remember, I'm not supposed to end there. My procedure required me, after getting the slope, I go on and calculate the constant using the formula K equal to GS. Now, since I know already S, I have got it, it is 5. Now, do I know G? Yes, you know it is constant. Maybe sometimes you use 10, sometimes you use 9.81, 9.8, depending, but that is the known value. So I use the G being 10, so my K will be 10 times 5, which gives me a 50 newtons per meter. Now, from my experiment, I have gotten what I was looking for. Now, how do I use it? I use it to give the advice or to make the conclusion. What is the conclusion? The conclusion is the spring constant of the spring in the lab, remember you are using the spring in the lab, lies in that range. It is true. And if it lies in that range, therefore, what does it mean? That is why you see I'm saying you are concluding and you are advising. You have concluded that it lies in that range, correct? Then what does it mean? Remember, we said if our spring lies in here, then it can be used to replace the damaged one. That is why we are adding this part. So you're concluding, then giving also the advice that now you're advising the farmers that therefore the farmers can use the spring in the lab to replace the damaged one. Alternatively, another person can just state it in this way, that the spring constant of the spring in the lab is, ignore this lies, is 50 Newton per meter, which lies in the required range. Hence, the spring in the lab can be used to replace the damaged one. So that is the conclusion and the advice. That is how you'll have done your experiment and this done given all the parts of the report, starting from the aim up to the last part, which is conclusion and advice. I had here some sample items But maybe before you look at these sample items, other sample items, these ones are not worked. They are just for practice. Maybe Mr. Kaziba, we can first have some questions.
Okay, thank you so much, Teacher Hewa. We're going to allow only two. And the first one is going to come from Namisi Indwa, Bobut SS. Bobut SS, unmute. Okay. In case we are failing to get Bobut, let's have brain set high. Brain set high.
Thank you, sir, for this opportunity. My first question is that how do we change the P notes to meters? And then the second question is like, is it a must that we have to start? We have to have the starting values as 0.0 on the graph. That's the question. Those are the questions. Thank you, sir.
Okay. Mr. Kaziba, do you want to have them at a go, or you want to have them
Yes,
answer?
Okay, let's have another one. Then okay. This one. Yes, Serada. Serada. Okay. St. Mary's Ediofe. St. Mary's.
The question is, you unmute. Where? Yes. Okay, the question is the answer supposed to be the correct answer, or you're supposed to get answers beyond the range? And if it is that way, is it wrong or correct?
Mr. Kaziba, can I answer those as we prepare to receive others?
Yes, it's okay.
Okay, the first one asked about changing P naught to meters. You know, when you're changing from centimeters to meters, you divide by 100. You're changing from centimeter to meter. This is under measurements, which is a senior one topic that you study in physics, conversion of units. So you're changing from centimeter to meter, you're supposed to divide by 100. And you realize if I'm dividing 60 by 100, 60.0, then the point just moves here and then here. So which gives me 0.6, but behind it, it had 2 zeros, which would be the 2 zeros here. That was about how you converted P naught to meters. You just dividing by 100. Then again, she asked about the starting values on the graph. That is it a must that always a graph should be starting from 0.0? It is not a must. However, you have to take note that in scenarios where you're going to take intercepts, then if let's say you want to get the intercept on the M axis, make sure your extension axis is starting from 0. If you're going to get an intercept on the extension axis, then make sure the M axis is starting from 0. I don't know if that answers you. We can only start from 0 if I need an intercept in that experiment. Other than that, it is not a must that you always start from 0. You can always start from a number which is a multiple of your scale and which is slightly less than your smallest value that you're going to plot. That is it. Then the other one asked about answers being correct. I think she was meaning, is it a must that my answer, for example here, if the interval given to me was between 40 and 60, is it a must that my answer should be 50? No, it is not a must. You get this answer from the calculation. And when it is not correct, I believe you cannot get penalized for not having the correct answer. That is why we have what we call the sources of errors. Now, what happens is, remember, the answer you have here dictates how you're going to conclude here. The answer you have there is the one that is dictating how you're concluding. If your answer was 70, now sincerely, will you now say the spring constant lies in the range? No, you will not say it lies in the range. So you will say the spring constant does not lie in the range. Now, if it does not lie in the range, then will you advise them to use it? Of course not. You will not advise. So you will advise also accordingly. Say, therefore, the spring in the lab cannot be used. So you conclude basing on the answers you get correctly calculated. And remember, the correctness of this calculation depends on how you carried out your experiment, taking care of the errors. When the answer comes out wrong, don't force it. Don't force it that because for you, you see the interval is supposed to be 45 to 60. Here you are having 10 times 7. You want to trust that the answer is 50. Yet you know very well 10 times 7 is 70. So don't force the answer to be correct. Do it the way it is. You will score for other skills like manipulating well, unit, but you may not get the one for correct answer. However, you can come here and again get your correct value basing on your advice. Remember here, we are not testing correctness. We are testing skills. Though correctness may be part of, accuracy may be part of what we test, but we are looking at how are you able to carry out an investigation and probably make conclusions based on your findings. So if you're according to your setup, it showed that the answer was a given value. Why do you want to change it? So don't change it. So let me hope I have answered those questions that were asked. Mr. Kaziba, back to you. Mr. Kaziba, are you there?
Yes, okay. Yes, teacher Ahewa. I think we take on just one. Arab Tech Computers. Unmute. Arab Tech Computers. Arab, I'm seeing the students there. Okay.
I see someone was asking, is it a must to draw a working diagram? Yes, you need a diagram because without it, of course, if you don't draw it, you don't die. But of course, you'll be missing some scores. Give us the scenarios. Someone is asking, what if I have divided and the answer I got is having many decimal points? That is co-method. How could I record it? That is where I said now data manipulation comes in. It is a long area. It is a bit lengthy. I can't talk about it now. Time is already bad. Maybe we shall have another session where we look at data manipulation. I see St. Elizabeth, they are pushing their hands up. I don't know if Mr. Kaziba, you can let them in as I read through the chat.
What's wrong with you?
Okay. Okay, I failed to get Arab Tech Computers. Arab, ask your question. Then maybe since I'm failing to get Arab, let me take on St. Elizabeth girls. Kid they talk.
Okay, sir. We just wanted to know which tense can we use? Can we use the length was or the length is measured?
I had already talked about that. I said the tense does not matter, but the best is present continuous. Like the length, you said about the length, about length. You said the length is measured. That is okay. Yeah.
Thank you, sir.
So even when you use past, it is still okay.
Okay, sir. Thank you.
Thank you,
sir. Thank you.
Mr. Kaziba, pick another one. St. Elizabeth, mute, then we, yeah, okay.
Okay, one more. Koboko, Nyalilo, SS Koboko.
I have two questions to ask. Okay. I have two questions to ask across. The first question is, if you are determining the scale in our school, it was like vertically it is highest minus lowest divided by 10, then it gives you the scale. Horizontally, it was highest minus lowest divided by either 10 or 9, depending on the number of graphs. So I suggest you saying here as openly that his scale is 2. I was wondering how that one came to existence. Secondly, okay, after getting the scale, you have to begin the origin. That's where my challenge is. I wanted you to help me in that origin. Thank you.
You're saying about the scale, I didn't figure clearly what the issue is, but about getting the scale, you saw me just mentioning. When we say the scale, this is what we mean by scale. The value from this one line to the next line, value from that line to the next line, from that line to the next line, that is what we call scale. When you look from 0 to 0.1, how much have I added? It is a 0.1. From 0.1 to 0.2, how much is it? It is still 0.1. From 0.2 to 0.3, how much is it? It is still 0.1. You get? That is what we call the scale. Showing the working there on the side is okay, but what matters is what have you indicated on the graph. Because sometimes you may find some students can indicate that my scale is going to be 0.1. When it comes here to rating, the student writes 0.20, 0.1, 0.2, reaches here, says 0.4, 0.5. You realize from 0.2, he or she jumped to 0.4, meaning he changed the scale. The scale was 0.1, 0.1, 0.1. Then all of a sudden changed it to 0.2. So that is what we mean by scale. Then the origin, I said you can start with any value that is, it must be a multiple of your scale. I repeat, it must be a multiple of your scale. If your scale is, let's say, 0.2, then I do not expect you to start here with a value, let's say 0.45. 0.45 is not a multiple of 0.2, because when you divide it, you can't get a whole number. So at least I would expect you to have maybe 0.44 or 0.40, which are multiples of 0.2. I don't know if there is, there is a lot of ideas we can talk about, but because of time, I'm trying to summarize. So that is about origin. However, I mentioned that it is important if you, in your experiment, you will need the intercept. Then you have to make sure that the axes start from 0 to be safe. Start all the axes from 0 if you want intercept in the graph. However, those who may be familiar with it, if you want intercept on mass, then make E to start from 0, the origin be 0. If you want intercept on E axis, then make sure the mass axis start from 0. That is it. Any other question, Mr. Kaziba? I see time is running against us.
Teacher Hewa, just summarize.
Okay. Yeah, so some people wanted me to share some of these other sample items. Maybe we shall share them in the group. Some of these items, like we had here the one for the resistor. Then we had here the one for focal length of a lens. And here we have the one for a beam. That is, let's say, an example, measuring mass of a meter rule in form of a beam. So we are going to share them in our groups, where maybe we shall have a look at them. So as I conclude, members, please just don't panic, relax, take your time. And the steps I have given you, make sure that your report is having those those parts that we have looked at. This is scientific investigation. You don't need to be copying from anyone because it is about skills, what you know. Because if you copy, then it can be seen from your work that the work is not yours, or you'll fail to show the skills. So just relax, take your time. I don't know, Mr. Kazevi, maybe we shall have some more time. We have another session where now we talk about, because I see many questions about significant figures, what data manipulation cases, reading of measuring instruments. That might be maybe for another session. But like I said, under variables, those who may want to have more ideas, please, you go to the YouTube channel, Teacher Hebo William. I have put that work there, that video. It explains, I've explained very well about variables. How do you get to identify variables? I think I don't have any much to add on that. I only thank you for being good students and for participating, and really wish you a good evening.
Okay, thank you so much, Teacher Hewa Williams, for the wonderful session, and thank you so much for taking us through this practical session. For the teachers, please make sure you do emphasize the degree of accuracy of the different measuring instruments that we use in the laboratories, because last year it was a challenge to the different children. So make sure you emphasize that area. Two, dear teachers, also do not encourage children to use the averaging approach whenever they are finding the different slopes and other values. Let's stick to the using of the graphic approach or the graphic method when they are finding the slope. Then please also emphasize the conclusion based on the results that have been analyzed. Yeah, it will be very key. But I also do understand that Teacher Hewa has still a lot that he wanted to share with us. We shall have time. We shall have time to get another session to take you through anything that has not been touched on. I know some of you have quite a lot of questions, but I know this week we may have time, but also we are going to share some resources on Wednesday concerning the different new updates about the physics practical. I know you have concerns. Some of you saw a circular circulating, but that circular did not come from UNEP, but we shall share with you some updates, other updates, or anything that may not have been touched on Wednesday evening or Thursday, but before this week ends. But also, I know we shall have time for Teacher Hewa to come back to share with us other things concerning the practical. So be patient, be patient. Let us first perfect other areas, but also we shall support you on this journey. For any questions that have not been answered, we shall be able to support you still. We shall share with you the program for this week. Let me see whether I can be able to get it. Give me a minute. Give me a minute to get for you the program for this week. So the program for this week will run like this. Yeah, hope you can see my screen. This is the program we are going to be running for this week. And please, we're using the same link. So tomorrow we shall have an ICT facilitation where we shall talk about the practical and the theory. Then we shall also have IRE, but where you see IRE, we are also going to have CRE at the same time. So on this day, on Wednesday, we shall use the same link, but we shall use breakout rooms. We shall have a room for CRE, we shall have a room for IRE. Then we shall also have entrepreneurship and then literature. But also we are going to create time within this week or next week to have other subjects, but we shall let you know. But I know we shall have biology practical coming on board very, very soon. So this is the program we shall be running for this week. So kindly take note. But I also understand that there are some subjects that you are interested in that maybe we have not yet shared with you. So we are also going to have those subjects brought on board, and we shall let you know when we shall have them. Then for some of these items that we keep sharing here, some of you are wondering where you can get them. So we are going to just give me a minute. So some of these items, we can still obtain them. Okay. Now, some of these items and some of these seminars that have been taking place in the different areas, we have uploaded them here. So whenever you get this Padlet link, you can access all these materials. Yeah, in case it is math, we have put here some solutions and some seminar items you can access for the different seminars that have been happening across the country. But also we are going to have all the videos uploaded here. Bit physics, you can come here, search for the solution, search for the questions, solution and the questions. Even the seminars that have just happened last weekend, you'll find the solutions here and then the seminar questions. So we are going to keep updating this link here. Even on Saturday when we had chemistry, you can find here the seminar questions and then they propose the solutions. So everything will be found on this link here. Just come check here all the seminars that are happening in the different schools across the country. You can access these resources on this platform, what we call the Padlet link. So you can use that link and then you can access all the materials. Otherwise, thank you so much. I'm happy to see Kangole girls from Karamoja. Thank you so much for attending, and all other schools that are joining in from the different parts of the country. Thank you so much once again, Mr. Teacher Heber Williams, for the wonderful session, and everyone and all the teachers that have been on the call. Thank you so much, and let me wish you a good evening, and bye-bye, everyone.
Bye-bye.
Okay, bye-bye.